thanks for watching, and today I want to illustrate the concept of Lagrange multipliers with two constraints to solve a very interesting problem. So, suppose you have two disks. Here's one that's centered at 0, 0 and of radius 1. And the other one that's centered at 5, 0 and of radius 2. What you want to do is to find the shortest and the longest distance between those two circles. So go find the shortest and longest distance between the circles. What does that mean? It means that among any points on this circle and this circle, which ones are the closest ones and which ones are the farthest ones? And of course I know that physically you can, the answer is here is the closest ones and here is the furthest ones, but I want to do this, using Lagrange multipliers just to illustrate how to do Lagrange multipliers basically. And what does that mean? It means that suppose you have a point here x1, y1 and a point x2, y2. We want to really maximize and minimize the distance between the two. D, which if you like is just given by the square root of the sum of squares of the two. So if you want, that's x1 minus x2 squared plus y1 minus y2 squared. And you take square root of that. That said, as is usual for Lagrange multipliers, if you minimize the square of the distance, it's the same thing as minimizing the distance, and vice versa. So you can just remove the square root, and this gives us our function. So f of x1, x2, y1, y2. That's the first thing. And moreover, well, we can't just pick any set of points, like those two would not be on the circles anymore. So x1 and y1 are constrained by being on the first circle. x2, y2 is constrained by being on the second circle. So what we do know is that x1 squared plus x2 plus, y1 squared actually. I was writing it correctly, but for some reason in my mind it was different. x1 squared plus y1 squared equals to 1, which is the same thing as saying this squared plus this squared minus 1 is 0. And this gives us our constraint, x1, x2, y1, y2. On the other hand, we have a second constraint here, because the second set of points has to be on this circle. So we have x2 minus 5 squared plus y2 squared equals to 4. So minus 4 equals to 0. And that gives us h of x1, x2, y1, y2. Which turns out that here we have a Lagrange multipliers with two constraints. Before I continue, let me tell you a little bit about the parameters. It seems oddly specific that I chose the point 0, 0, the radius 1, and also to have this point on the x-axis. But it turns out the most general case is almost like that too. Because up to a translation, it's okay to assume that you are at the origin. Because otherwise you shift your coordinate system to make this work. Moreover, if you have any radius here, you can just divide by that radius and still get a circle of radius 1. So what I'm saying, it only matters what this radius is relative to this one. So we have a leeway, we can choose this to be 1. And also, if this point is somewhere else, like here, you can just rotate your coordinate system and make this point be on the x-axis. So it is actually not much of a loss of generality. The only thing that makes us lose generality is this 2. And in fact, if you have a radius of 5 or something, it becomes a completely different problem. So it turns out this is almost the most general case. All right. And now the next step is we have our functions, we have our constraints. Let's now write the Lagrange equations, which usually is gradient of f is lambda gradient of g. But because we have this new constraint h, we have to write a similar term for h. So if you want plus lambda prime gradient of h, which I'll just write as mu gradient of h. And our two constraints, g and h. Those are the Lagrange equations, but now let's write those, specifically, concretely in terms of our derivatives. And very important, this gradient here, it's the gradient of x1, x1, x2, y1, y2. So we have to differentiate all of that junk with respect to 4 variables. Which looks horrible, but I believe in you, and also there's a lot of simplifications. So, differentiate f with respect to x1, it becomes 2 times x1 minus x2. And now, lambda gradient of g, so gx1, which becomes lambda 2x1. And the nice thing is, h doesn't depend on x1 at all, so this gradient is 0. And now let's do the same thing. So gradient x2, so it's 2 times x1 times x2, but with this minus, becomes 2 times x2 minus x1. And this now doesn't depend on x2, so it's lambda times 0. And then plus mu times 2 times x2 minus 5. And now let's just do the same spiel again, but with y1. So this becomes 2 times y1 minus y2 equals to lambda 2y1 plus mu. No y1s, so 0. And lastly, 2 times, if you want y2 minus y1, that's lambda times 0 plus mu times 2 y2. Looks absolutely horrible, but there are a lot of simplifications. You see 4 of the terms are 0, and the 2's cancel out. So bang, 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 bang. Okay. 8 bangs here with 4 zeros. So it's a 12 bang party or something. All right, and we're left with x1 minus x2 equals to lambda x1. x2 minus x1 is mu to x2 minus 5. y1 minus y2 is lambda y1, and y2 minus y1 is mu y2. Very good. We have our set of equations, which we have to solve simultaneously. And remember, we also have the constraint. So, usually very hard to do. Here it's extremely hard to do, but let's just do it step by step. So we have 4 equations, 1, 2, 3, 4. Let's deal with the easier set of equations first. So 3 and 4. Well, for 3, the nice thing is you can solve for y2 in terms of y1. Put y2 here, lambda y1 on the left-hand side. So y1 minus lambda y1. So y2 is 1 minus lambda y1. Which is good. It tells you that once you found y1, you can solve for y2. Now, let's do the same spiel with the fourth equation, I guess. y1 is, if you want, 1 minus mu y2. Again, very similarly. that said, we can simplify this because y2 is also equal to 1 minus lambda y1. So it becomes 1 minus mu, 1 minus lambda y1. And now just solve for y1. So y1 of 1 minus this factor equals to 0. And you might say, oh my god, y1 is 0, not so fast. Because it could be that this factor is 0, and that happens in Lagrange multipliers. And therefore, later we will have to deal with cases. But before we do that, let's deal also with the other two equations. So maybe now you see the pattern. So x2 then becomes 1 minus lambda x1. And also for this equation, slightly more complicated, but what we get is x1 is x2 minus this junk, so 1 minus nu x2 plus 5 nu. Again, I expanded this out as mu x2. I put this on the left-hand side to get 1 minus mu x2, and also I put this minus 5 nu on the left-hand side to get 5 nu. And not only that, we can use again the same thing. Because you can solve for x2 in terms of x1, this becomes 1 minus nu, 1 minus lambda x1 plus 5 nu. And so just as before, x1 times 1 minus nu, 1 minus lambda equals to 5 nu. So again, if this factor were non-zero, we could actually solve for x1. But again, not sure. Okay, good. So we took those four equations, we rewrote them in a simplified manner, and let me just write them again. So we have x2, it's 1 minus lambda x1. x1 times this factor, 1 minus nu, 1 minus lambda equals to 5 mu. y2 times 1 minus, y2 equals to, is that correct? Yeah. y2 equals to 1 minus lambda y1, and y1 times 1 minus nu, 1 minus lambda equals to 0. So those become our new equations, 1, 2, 3, 4. And remember, we also have the constraint, which we'll talk about in a second. So let's just call them 1, 2, 3, 4 again. Alright, now as promised, we have to deal with cases. Let's first assume this factor is 0. Case 1, assume that 1 minus nu, 1 minus lambda equals to 0. And let's just play around with this a little bit. If this factor is 0, then this factor is also 0. So 2 would imply x1 times 0 equals to 5 nu. So 5 nu is 0, so nu equals to 0. Okay, and then what we get is that, yes, if nu is 0, then we get that, if mu is 0, this is 1, and so we get 1 minus lambda equals to 0. And so, if you want 1 minus lambda equals to 1, and this is useful because we can just plug it into 1 and 3, because if this is 1, then we get that x2 is x1 and y1 is y2. So x2 equals to x1 and y2 equals to y1. So by 1 and 3. But the interesting thing is it tells you in fact that the point x1, y1 equals to x2, y2. And now you could use the constraints to figure out that this is nonsense, but just think of it in terms of the problem. So this is this circle of radius 1, and this was the point x1, y1. This is the disk of radius 2, and this is x2, y2. Well, if those 2 points are equal, this is kind of nonsense because there is this distance here. And in fact, if they're really equal, it would be a contradiction. Because again, this is the 0.50, this is 0.00. Because if the points are equal, this would mean that this distance, of course, is 1, which is the radius. This distance would be 2, which is the radius. But if those 2 points are equal, those 2 radii, it would be the same as the distance between 0, 0, and 5, 0, and it would be 5. And therefore, you would have a triangle with sides 5, 1, and 2, and that's not possible due to the triangle inequality. Triangle inequality always says that the sum of the distances of 2 sides has to be greater than or equal to the third side. So here we have a contradiction. It's a good contradiction because it tells you that we don't have the singular case where this factor is 0. So in fact, it is non-zero. But again, algebraically, just plug it into the constraints. You can actually solve the equations, and you find that it makes no sense. Okay, and so case 2, the good one, actually, assume that this is non-zero. So 1 minus nu times 1 minus lambda. Assume that this is not equal to 1. I guess 1 minus this is not 0. This is fantastic because now in 4 you can divide by this number which is non-zero. So 4 gives you y1 equals to 0. And remember, the greatness of equation 3 was that once you have y1, you can solve for y2. So 3 implies y2 is 0, and you could solve for x1 and x2 using equations 1 and 2, but it turns out because you already have those, you can just use the constraint, so I think that's a bit easier. So now, because y1 and y2 are 0, we get, x1 squared plus y1 squared equals to 1, but this is 0, which tells you that x1 is plus or minus 1. And similarly for the other constraint, we have x2 minus 5 squared plus y2 squared equals to 4. This is 0, so this tells you that x2 is, 5 plus 2 or 5 minus 2, so it's 3 or 7. Which gives us, if you want, 4 possibilities of points. If you want, either we have the point 1, 0, 3, 0, minus 1, 0, 3, 0, 1, 0, 7, 0, and minus 1, 0, 7, 0. And now let's go back to our original figure and see which one gives you the maximum and the minimum. So, if you want, you can also calculate the distance. So here the distance would be 3 minus 1. So square root of 2. No, never, sorry. Distance between the two is just a difference. So d is 2, and here is d is 4, d is 6, and d is 8. And so already just algebraically you can see that the smallest distance is 2, so the minimizers are 1, 0, 3, 0, and the biggest distance is 8, and those are the maximizers. And as I said, let's go back to our figure to see if this makes sense. So we have the center 0, radius 1, and then center for 5, 0, and radius 2. The first possibility gives us, in fact, those 2 points, right? 1, 0, and 3, 0. And indeed, they give us the smallest distance. On the other hand, the second choice gives us those 2 things, minus 1, 0, and 3, 0, which is sort of intermediate, so it doesn't work. On the other hand, we have those 2 things, so 7, 0, and 1, 0, this distance, which is also intermediate, or the last thing is minus 1, 0, and 7, 0, and yes, that does give us the biggest distance. So it does work. That's what I want to say. Here's a cool thing about Lagrange multipliers. Of course, in general, it's very hard to, go through all the equations and figure it out, but it's sort of an artwork here. Alright, so if you like this excursion into Lagrange multipliers and want to see more math, please make sure to subscribe to my channel. Thank you very much.